Time is the most important thing for GNSS positioning. Just imagine the signal from the satellites are traveling at a speed of light that is about 300,000 km per second, equivalent to 186,000 miles per second, and they are coming into our receiver at a precise time. And if this time is delayed by even 1 second, we can be halfway to the moon. So, how precise our time is going to be? If I take 1 millisecond or 1,000th part of a second, then our position can be out by 300 kilometers or about 186 miles. Let's say you are standing at a railway crossing and a train is passing by you at constant speed. A passenger inside the train is playing with a ping-pong ball bouncing between two boards. From the passenger's perspective, the ball is moving straight up and down as she, the ball, and the boards moving forward at a constant speed. From your perspective, the ball is not moving up and down, but the path of the ball is taking a triangular shape as it travels between the boards. From the passenger's perspective, the ball is moving a short, straight distance and it takes about a second to travel. But from your perspective, the ball is traveling longer distance. So if the time between the bounce remains same, to travel a long distance, the ball has to speed up, right? Let's assume that in place of the ping-pong ball, it is a beam of light bouncing between two mirrors. From the passenger's perspective, nothing changes. The beam of light travels back and forth in shortest distance possible. But from your perspective, the beam of light is taking longer distance to travel. So do you think the speed of light has to increase to catch up with the moving mirrors? We know that the speed of light is constant for all observers. So to keep the equation distance is equal to speed multiplied by time, we must make the time go slow. Moving time runs slower than the stationary time. The time did pass at a different rate for the passenger than it passed for you as an observer standing stationary. Einstein's theory suggests that there is no such thing as absolute time. Now the passenger on the train and you as an observer will not notice this time difference because the amount by which time slowed down for the passenger was minuscule as the speed of the train is very small compared to the speed of light. But if you see a satellite moving in space at 14,000 km per hour and you compare the time on the satellite with your time standing on Earth, the difference becomes obvious. Every day the atomic clocks on the satellite slows down by 7 microseconds, and this is called Einstein's special relativity. Fascinating, isn't it? But what is the real life scenario here? Perhaps you know that we use GPS in our everyday life, don't we? And the satellites are some 20,200 km above the Earth's surface and they are moving at 14,000 km per hour speed. Fast enough to make quite a bit of difference in their atomic clock. How much you ask? Well, it's about 38 microseconds each day and they are getting faster than the atomic clocks on Earth. But how does that matter, you ask? Well, it matters if you are using GPS positioning. 38 microsecond is equivalent to 11.39 meters, which can pretty well make the Google map unusable. If you have a quartz watch, it might lose half a second every day. But if you are working with precise positioning, then 1 microsecond or 1 millionth of a second can deviate your position by 300 meters. Our precise position comes from the satellite into our GPS devices, and they have an atomic clock to make sure that this time deviation does not happen. What most of us do not know that these atomic clocks on the satellite that are moving in the orbit at about 14,000 km an hour can deviate a lot than the atomic clocks that are on Earth. But how does the time deviates in a satellite? So what is an atomic clock? Atomic clock is the cesium atom 132 kept in a specific chamber and it vibrates over 9 billion times every second, and we know that vibration precisely and we can calculate time that precisely. But what about our clock? Our clock can be very cheap on our receiver, on our mobile phone. As soon as our clock or the receiver latches onto a satellite in the orbit, it synchronizes automatically. But there is a problem. The satellites are not on Earth. The atomic clock on the Earth and the atomic clock on the satellites about 20,000 kilometers above the Earth's surface has a significant error between them. All thanks to Mr. Einstein. Let me explain. Einstein's theory of general relativity says that the clock will run faster if they are not into the influence of any gravity. So the satellites are in microgravity. So the atomic clocks on the satellites, they are actually running faster than the atomic clocks kept here on the Earth. How much faster, you ask? It is running about 45 microsecond every day. In every 24 hours, the atomic clocks on the satellites, they run 45 microseconds faster. Okay, I told you 1 microsecond is equivalent to 30 meters of error. So 45 microsecond is a huge. But then Einstein also provided us with theory of special relativity. As per Einstein's theory of special relativity, when an object is moving at a fast speed, it loses time. Time compresses for him. That is the Einstein's theory of special relativity. So the satellites are moving at about 14,000 km per hour at a breakneck speed in the orbit. Every day, every 24 hours, the satellites are losing about 7 microsecond. And if we calculate both of them, on an average, the satellites are gaining about 38 microsecond every day. And we need to adjust those timings every day into each and every satellites. What if we can travel in time and move at almost the speed of light? If you can move at 99.9% of the speed of light, then time for each day on Earth will be 1.074 hours for you. So if you travel at the same speed for 16.3 days and come back to the Earth, then as per the Earth's time, 1 complete year has gone by. You see, we do not think about the time, we do not think about the value of 1 second. But each of them matters. When you are doing a navigation with your Google map, this time matters, or you will never reach your destination. So stay curious and always ask questions. I'll see you in the next video.